Today we are going over 9.3 rational functions and their graphs. So let's take a look at some properties here. We have an inverse variation is an example of a rational function. And we should think of something that is rational as a fraction. Think of it as a fraction. So if we have something where it's p of x over q of x, then that means that is two different types of equations and it's a rational function. We know that q of x, the one in the denominator, that cannot be equal to 0 because we cannot have 0 in the denominator. Okay, so we're going to take a look at some points of discontinuity here, and we're going to look at finding the values of x that makes the denominator 0. Those will be the points of discontinuity. So we're going to take a look at the denominator here, and we're going to say this denominator, x squared plus 2x plus 1, that cannot equal 0. Because we cannot have 0 in the denominator. So then what we'll do is we'll factor this and we'll say, okay, what multiplies to 1 and adds up to 2, that's going to be x plus 1 times x plus 1, and that cannot equal 0. Since they're the same binomial, then we just can solve for one of them, so therefore x cannot equal -1, and that is our point of discontinuity. This is going to lead to later on talking about the vertical asymptotes. But for now, we're just going to say it is a point of discontinuity. Meaning, if we were to graph this, this is going to be a point where we will have a jump or a hole or a asymptote in our branches. Okay, over here we'll have the denominator of x squared plus 1. We know that cannot equal 0. We'll solve for x here. X squared cannot equal -1. Once we take the square root here, whenever we take the square root, it's a plus and a minus. And it's the square root of -1, which is an imaginary number, plus and minus I, which just means this is an imaginary number, so this has no points of discontinuity because we didn't get any real numbers when we solved for x. Okay, so moving on here. So we're going to look at the asymptotes or holes in the given function. So here's what we're going to do. We're first going to, just like we did in the previous example, we're going to take the denominator and we're going to say this cannot equal 0. So we know that we have two of them because of the squared. So we have x minus 2 times x minus 2. That cannot equal 0. Therefore, x cannot equal 2. When I add 2 over, x cannot equal 2. Okay, so now if we look here, we want to look to see if I can factor this. And if I factor this, I'm going to cancel out my x minus 2's in the numerator and in the denominator because we have one in the numerator and the denominator. So in the numerator, I just have a 1 left over, and in the denominator, I have x minus 2 left over. So this is what you would actually graph when you go ahead and graph it. And this x equals 2 is going to be our vertical asymptote. So that means when I actually go ahead and graph it, it's just saying, do we have any asymptotes or holes in this? We do. It's at x equals 2, and it's a vertical asymptote for this. Okay, so moving on here, we're looking at, so this one here is already factored for us. So before you go ahead and cancel things out, you still want to take the denominator and say this denominator cannot equal 0, so therefore we get x cannot equal 2 and x cannot equal -1. So since we have these two, we first would originally say that they are vertical asymptotes, but now we're going to go ahead and go back to the original problem here and cross out what we can. So since we have an x minus 2 over x minus 2, we're going to cancel that out. So since this part was canceled out, that means this is no longer a vertical asymptote. It is now a hole in the graph. So we're going to be left with, after we cancel these out, in the numerator we'll have an x plus 3, and in the denominator I'll have an x plus 1. So this is what you would actually graph when we go ahead and graph these. And we're going to find the hole by taking this 2. We know the x part is a 2. And we're going to plug this 2 into the simplified version of our equation. So therefore we get 2 plus 3 over 2 plus 1. That's going to give us a 5 over 3, or 1 2/3. So at 2 5/3, you're going to have a hole, and this is a point of discontinuity. And at x equals -1, this is going to be our vertical asymptote. And that's because this did not cancel out and it's still in the denominator. So we have a hole here and we have a vertical asymptote at x is -1. Okay, so still moving on and doing a similar thing here. We're finding vertical asymptotes and holes for the graph. We'll do one more like this. We say the denominator cannot be 0. We make our t-chart here, and x cannot be 2 and x cannot be 3. And these are both vertical asymptotes because they do not cancel out. This one here, we know that the denominator cannot be 0. So x cannot be a 2, but then once we go back and cancel things out, we're left with y equals x minus 1. So therefore, your x equals 2 is going to be a hole. So we know the x part is a 2. We'll find the y part by plugging it in to the simplified version. And 2 minus 1 is a 1. So therefore, there's a hole at 2, 1 for this. So you would graph y equals x minus 1, and you would make a hole at 2, 1. Okay, horizontal asymptotes. So there's going to be 3 rules for finding horizontal asymptotes. So the horizontal asymptote is going to be y equals 0, because when it's a y equals a number, it's a horizontal line. That's going to be y equals 0 when the degree of the denominator is greater than the degree of the numerator. For example, we will have y equals 1 over x, which is an inverse variation and a type of rational function. So here, in the denominator, the degree is 1 because x to the first. And here, the degree is 0 because there's no variable. So if there's no variable, that's the same as x to the 0, and x to the 0 is just a 1. So therefore, the degree is bigger in the denominator, and therefore, our horizontal asymptote is y equals 0. Next one is going to be when the degree is the same or equal in the numerator and the denominator. So if that happens, for example, if I have y equals x plus 1 over x minus 3, the degree here is a 1. The degree is the highest exponent, 1. The degree here is also 1. So that means what you're going to do is you're going to take a over b, meaning the coefficient of x over the coefficient of x. And therefore we get 1 over 1, which is just a 1. So your horizontal asymptote is y equals 1. And then finally, if the degree of the numerator is greater, then you have no horizontal asymptotes. For example, if we have y equals x plus 1, this is a line. So here, the numerator is x plus 1, the denominator is just a 1. So the degree is a 1 in the numerator and it's 0 in the denominator because there is no variable. So therefore, since the degree is bigger in the numerator, then there's no horizontal asymptote because it's a line. Okay, so finding vertical and horizontal asymptotes here. So we can start with the vertical asymptotes by taking the denominator and setting that equal to 0, therefore x equals 1. And we also need to look to see if we can factor anything. We could take out a -2 here and get x minus a 3, but that still wouldn't cancel it out. So x equals 1, that's going to be our vertical asymptote, because x equals a number is a vertical line. And then for the horizontal asymptotes, we look at the degree. We say, is it bigger in the numerator, the denominator, or the same? And in this case, it's the same degree. The degree here is 1 and a 1. So if it's the same, we do a over b. The coefficient in the numerator, -2, over the coefficient in the denominator, which is a 1. So the horizontal asymptote is y equals -2. Okay. Next one, we have, we could do this one here. So our vertical asymptotes, we'll set the denominator equal to 0. The vertical asymptotes will be a -3 and a 4. That is an x there. Okay. And those are the vertical asymptotes. Here, we have a degree of 1 here, but in the denominator, we have 2 x's. Meaning if I was to multiply this out using FOIL, I would have an x squared in the denominator. So therefore, the degree is bigger in the denominator, and when the degree is bigger in the denominator, you always have y equals 0 as your horizontal asymptote. All right, and let's see. Okay, so now we can actually sketch this. So we said the vertical asymptotes here are -3 and 4. So we can go ahead and sketch those. So we're going to have -3 and 4, putting those in here. So we'll have -3 is 1, 2, 3 right here. And we'll also have 4, 1, 2, 3, 4. Those are our vertical asymptotes. And then we can look at the denominators, and we know that since I have the degree is bigger in the denominator, then that means that I'm going to have my horizontal asymptote as y equals 0. So we can graph that in also. And that would be y equals 0. Make that one a little thicker so we can see it. There we go. And then what we're going to do is we're going to break it up into branches. So we have here different branches. So we're going to look at branch 1 is going to be in this quadrant here. This will be branch 1. And branch 1 will be to the left of -3, because this is x equals -3. This is x equals 4. So we'll have branch 1. We plug in points to the left of -3. So when we do that, we can plug in points. For example, we can plug in -4, and we can plug in -5, and so on. So we'll plug in -4. So we get -4 plus 2 is a -2. -4 plus 3 is a -1 times -4 minus 4. -4 minus 4 is a -8. So we get -2 over 8, or a -1/4. So we can plug that in. -4, -1/4. So already we know that it's going to be down here. And since we already have these asymptotes drawn in, we know that it's going to be approaching our asymptotes. So it'll look something like that. For branch 2 here, we're going to plug in values that are between -3 and 4, those asymptotes there. And if we look here, this numerator is also giving us another key feature. This numerator is going to be telling us where it crosses the x-axis by setting it equal to 0, and we'll get a -2. So this is going to be our x-intercept here. So we already know we're going to cross it at -2. And these asymptotes are only for certain branches. So when we graph that, we'll plug in points. So we already have -2 is going to be 0. We can plug in 0. And we can plug in 3. So when I plug in 0 into my equation, I'll get 0 plus 2 is a 2 over 3 times a -4 is a -12, and then we'll get a -1/6. So we'll get -1/6 there. And when I plug in my 3, I'll get 3 plus 2 is a 5. 3 plus 3 is a 6 times a -1. So this is 5 over -6, or -5/6. And then we can go ahead and sketch that. So this will be 0, -1/6. And then 3 is still really low here, so it'll be somewhere over here. And then it's going to start approaching. So it's coming down here. It's going to start approaching your asymptotes like that. The last branch is going to be B3 for branch 3, and we know we have to plug in values that are bigger than 4, so we can plug in 5 and 6 and so on. And really we just want to see, is the branch going to be positive above or negative below? So let's see here. We'll plug in 5. 5 plus 2 is a 7 over 5 plus 3 is 8 times 5 minus 4 is a 1, and that's a positive, so 7/8. So this will be a 7/8. So we get 5, 7/8. And then we know that it's going to be approaching our asymptotes. So we'll have it approach like that. And that is 9.3.